Welcome everyone. Today, we are diving into a fascinating new approach to AI called modeling distinct human interaction in web agents. If you have ever watched an AI agent confidently mess up a task while you scramble to hit the stop button, this is for you. We are going to explore how we can move away from that frustrating, reckless autonomy and towards intuitive collaboration using two new tools introduced by researchers from Carnegie Mellon and Duke, CalCorpus and PlowPilot. Right now, the AI industry has a bit of a Goldilocks problem when it comes to agent autonomy. On one extreme, we have reckless autonomy, where the agent just charges ahead, ignores risks, and forces you to panic stop its execution. On the other extreme, we have nagging confirmation, where the agent is so timid that it asks for your permission at every single step, which creates a huge burden for the user. What we actually want is right in the middle, intuitive collaboration. This is where the agent seamlessly predicts exactly when to ask you for help, making handoffs smooth and natural. To figure out how to reach this middle ground, the research team created a dataset called CalCorpus to map out the real landscape of human-agent collaboration. They recorded 20 real users completing 400 different web navigation trajectories. This resulted in a massive dataset containing over 2,700 agent actions and almost 1,500 human actions, spanning both standard benchmark tasks like booking flights and unconstrained, free-form tasks. Crucially, they meticulously annotated the exact moments when humans felt the need to step in and intervene. So, why exactly do users intervene? The study found three main drivers. First is error correction, like when the agent gets stuck in a loop or clicks the wrong element, and the user has to physically stop it and redirect it. Second is preference refinement. Sometimes our initial instructions are vague, like simply asking for cheap flights, and we have to jump in mid-task to clarify what we actually want. And third is assistive takeover. Some websites are just too complex for current AI, think CAPTCHAs or highly dynamic pages, so the user has to manually take the wheel to help the agent out. Understanding this why is the first step to predicting the when. But here is the really interesting part: not all users intervene in the same way. The researchers identified 4 distinct user archetypes. The observer or hands-off user trusts the agent completely and rarely steps in. On the flip side, the hands-on user acts like a micromanager, making frequent and intense interventions. Then there is the mender or takeover style. They watch silently and then just jump in at the very end to finish the task manually. Finally, the mediator or collaborative user balances things out, making modest adjustments and then smoothly handing control back to the agent. When you map these user types out based on how often they intervene versus how often they hand control back to the AI, a very clear picture emerges. User behavior isn't just random, it is highly structural. These interaction patterns actually remain stable across totally different tasks. This is a massive breakthrough, because if human intervention behavior is structured and predictable, it means we can actually train machine learning models to anticipate it. That brings us to the core technical challenge, the intervention prediction task. Here is how the researchers set it up. At each step, they feed a multimodal large language model 3 inputs: the history of the task so far, a current screenshot of the page, and the web page's underlying accessibility tree. The model's job is to output a simple binary prediction: should the agent safely continue, or is it highly likely the human wants to step in, meaning the agent should stop and ask the user. Standard accuracy isn't quite enough to measure success here, because in collaboration, timing is everything. If the agent asks for help too early, it's annoying. If it misses the moment entirely, the task fails. To measure this correctly, the team introduced the perfect timing score, or PTS. PTS perfectly balances accuracy with annoyance by penalizing the model based on how far off its prediction is from the actual ground truth intervention point. So, how do our current AI models stack up on this new metric? The results might surprise you. Massive, proprietary generalist models like GPT-4o actually perform quite poorly, generally failing to intervene when needed. However, when the researchers took a smaller, open-weight model, like Gemma 27b, and specifically fine-tuned it on the cow corpus interaction data, it achieved state-of-the-art performance. These specialized small models significantly outperformed the giant proprietary models. Why do these massive, intelligent models struggle so much with this task? It really comes down to how they are trained. Generalist models are heavily trained to be polite, helpful assistants. Because of this, they suffer from what the authors call silence bias. They are overly conservative, hesitant, and reluctant to predict their own failure. Fine-tuned models, however, are trained directly on real human interaction data. They actually understand the specific rhythm of human-agent handoffs and know exactly when it's time to hit the brakes. We can take this even further by actually adapting to the user. Remember those 4 archetypes we talked about earlier? It turns out that model performance is maximized when you match the model to the user's specific collaboration style. For instance, a hands-on user needs a model that has a high tolerance for constant interruption. A takeover user needs a model that knows when to just resign control entirely. By personalizing the model, the collaboration becomes much more aligned with human preferences. To put all of this incredible research into practice, the team built PlowPilot, an intervention-aware web agent. Instead of blindly executing actions or constantly nagging you, PlowPilot proposes an action and internally queries the intervention prediction model. If the model predicts a high likelihood that you'd want to step in, it politely prompts you for confirmation. If not, it executes the action automatically. The result is exactly what we wanted: fewer interruptions, better timing, and perfectly preserved user control. The team then validated PlowPilot in the real world with real users. They compared a baseline agent, where the user has to constantly watch the screen and manually hit stop, against PlowPilot, which pauses automatically right before risky steps. They measured this across a mix of standard and free-form tasks using 20 annotators to gauge the system's perceived utility. The results from the user study were incredibly positive. Users reported an impressive 26.5% increase in overall utility with PlowPilot compared to the baseline. Annotators noted that the agent successfully avoided interrupting them unnecessarily, and that having the agent anticipate their interventions made them feel far more in control of the automation. Anticipating human intervention genuinely leads to more adaptive and effective collaboration. To wrap things up, this research clearly shows us that the future of AI isn't just about pure, reckless autonomy, it is about collaboration. With cow corpus, we finally have a dataset mapping the when and why of human intervention. We've seen that smaller, fine-tuned models can actually beat giant LLMs at reading the room. And ultimately, it proves that true trust between a human and an AI is built by optimizing for the partnership and knowing exactly when to ask for help. Thanks for watching.